Part 3: Compression and Bending Structures, or Cloud Cap D Towers and the Stability of Masonry. What are you able to build with your blocks? Castles and palaces, temples and docks. R. L. Stevenson, A Child's Garden of Verses. As we have seen, unless one is as clever as nature is, the whole business of making tension structures is set about with difficulties, complications, and treacherous traps for the unwary. This is especially the case when we want to make a structure from more than one piece of material, so that we are faced with the problem of preventing it from coming apart at the joints. For these reasons our ancestors generally avoided tension structures as far as they could and tried to use constructions in which everything was in compression. Much the oldest and the most satisfactory way of doing this is to use masonry. As a matter of fact, the immense success of masonry buildings has really been due to two factors. The first is the obvious one about avoiding tension stresses, especially in the joints. The second reason may be less obvious. It is that the nature of the design problem in large masonry buildings is peculiarly adapted to the limitations of the pre-scientific mind. Out of all the different kinds of structures which might be made, the masonry building is, as we shall see, the only one in which a blind reliance on traditional proportions will not automatically lead to disaster. This is why, historically, masonry buildings were by far the largest and most imposing of the works of man. The desire to build cloud cap D towers and solemn temples goes far back into history and indeed into prehistory. There is a quotation from Genesis about the Tower of Babel at the head of chapter 1. It may be remembered that this was a project to build a tower with its top in the heavens. However, I do not think any theologian has ever inquired to what height such a tower could really have been built. Nearly all the load upon the walls would have been due to the effect of their own weight. And one way of looking at the problem is to calculate the direct compressive stress which would be caused near the bottom of the tower by the vertical dead weight of the masonry. A limit will be set to the height of the structure when the bricks begin to be crushed by the superincumbent weight. Now brick and stone weigh about 120 pounds per cubic foot, 2,000 kilograms m3, and the crushing strength of these materials is generally rather better than 6,000 psi or 40 mn/m2. Elementary arithmetic shows that a tower with parallel walls could have been built to a height of 7,000 feet or 2 kilometers before the bricks at the bottom would be crushed. However, by making the walls taper towards the top, it could have been made much higher still. This is more or less how mountains work. Mount Everest is 29,028 feet or about 8 kilometers high and shows no signs of collapsing. Thus a symbol which actually exists today is probably the New York Trade Center, which is only about 1,350 feet or 400 meters high, and this, like other skyscrapers, could be said to be cheating, since its structure is made of steel. The Great Pyramid and the highest cathedral spires reach a little more than 500 feet or 150 meters, but very few other masonry buildings are more than half so tall. The great majority are much lower still. Therefore the compressive stresses in everyday masonry due to its own vertical dead weight are very small indeed. In general they are seldom more than 1/100th part of the crushing strength of the stone, and so this factor is not, in practice, a limitation upon the height or the strength of buildings. However, to be biblical again, the Tower of Siloam, which was probably not particularly high, fell and killed 18 people, and it is notorious that in spite of the confidence of builders and architects, walls and buildings do fall down unexpectedly. They have been doing so for a very long time and they still sometimes do so today. Since masonry is heavy, people often get killed. If walls do not collapse because of the direct crushing stress upon the material, why do they fall down? Once again, we can learn from what children do. When we were very young, most of us played with bricks, and about the first thing we did was to build a tower by piling one brick upon another rather erratically. Usually, when the tower had reached a modest height, it fell down. Even the child knew perfectly well, although he could not have expressed the idea in scientific words, that there was no question of the bricks being crushed under a compressive stress. The actual stress in the bricks was negligible. What happened was that the pile of bricks tipped up and fell over because the tower was not straight and vertical. In other words, the failure was due to lack of stability and not to lack of strength. Although this distinction soon becomes evident to young children, it is not always clear to builders and architects. For the same reason, the reflections of art historians who write about cathedrals and other buildings are apt to make rather distressing reading. How reverend is the face of this tall pile, whose ancient pillars rear their marble heads, to bear aloft its arched and ponderous roof, by its own weight made steadfast and immovable, looking tranquillity. It strikes an awe and terror on my aching sight. William Congreve, The Mourning Bride. There was only one culture in Queen Anne's time, and there is very little doubt that Congreve, 16701729, talked and drank with Vanbrugh, who wrote plays and designed Blenheim Palace, and also with Sir Christopher Wren himself. To all these people it was perfectly clear in a general kind of way that what kept a building from tipping up and collapsing was not so much the strength of the stones and mortar as the weight of the material, acting in the right places. However, it is one thing to be aware of this in a general kind of way and another to understand what is happening in detail and to be able to predict just when a building is safe and when it is not. In order to get a proper scientific understanding of the behavior of masonry, it is necessary to treat it as an elastic material, that is to say, one must take into account the fact that the stones deflect when they are loaded and that they obey Hooke's law. It is also a considerable help, though perhaps not absolutely essential, to make use of the concepts of stress and strain. At first sight it does, of course, seem improbable that solid brick and stone should deflect to any significant extent under the loads which occur in a building. In fact, for at least a century after Hooke's time the common-sense view prevailed, and builders and architects and engineers persisted in ignoring Hooke's law and treating masonry as if it were perfectly rigid. In consequence, their buildings sometimes fell down because they got their sums wrong. As a matter of fact, the Young's moduli of brick and stone are not particularly high, and, as one can see from the bent pillars in Salisbury Cathedral, Plate 1, the elastic movements in masonry are by no means so tiny as one might suppose. Even in an ordinary small house the walls are likely to be shortened or compressed elastically, in the vertical direction, by something like a millimeter under their own weight. In a large building the movements are naturally much greater. Incidentally, when the house is shaken by the wind during a gale, you are not imagining the effect, the house is being shaken by the wind. The top of the Empire State Building sways something like 2 feet during a storm ***. The modern analysis of masonry structures is based upon simple Hookean elasticity and also upon 4 assumptions, all of which turn out to be justified by practical experience. These are: 1. That the compressive stresses are so small that the material will not be broken by crushing. We have already discussed why this is so. Because of bricks or stones sliding over each other. In fact, no sliding movements at all will take place before the structure collapses. 4. That the joints have no useful tensile strength. Even if, by chance, the mortar does have some strength in tension, this cannot be relied upon and must be neglected. Thus the function of the mortar is not to glue the bricks or stones together but simply to transmit the compressive load more evenly. As far as I know, the first person to take the elastic deformations of masonry into account was Thomas Young. Young considered what would happen in a rectangular block of masonry, such as a piece of a wall, when it had to carry a vertical compressive load, P, let us say. In what follows I have simplified Young's arguments by translating them into the language of stress and strain, which of course was not available in his time. As long as P acts symmetrically along the center line, that is, down the middle of the wall, then the masonry will be compressed uniformly, and, because of Mr. Hooke, the corresponding distribution of compressive stress across the thickness of the wall will also be uniform. Figure 1. Suppose, now, that the vertical load, P, becomes a little eccentric, that is to say, it no longer acts exactly along the center line. Then the compressive stress can no longer be spread evenly but must be higher on one side than on the other so as to react properly against the load and keep it in balance. If the material obeys Hooke's law, then Young showed that the stress will be distributed linearly and the stress distribution diagram will look like Figure 2. So far the mortar in the joint is quite happy because the whole width of the joint is still safely in compression. However, if the position of the load is displaced still further from the center, in fact to the edge of what is called the middle third of the wall, then a situation like Figure 3 will arise where the load distribution is now triangular and the compressive stress at the outside edge of the joint is 0. Figure 1. Load P acting in center. Figure 2. Load P slightly eccentric of joint AB but within the middle third of AB. This, in itself, does not matter too much, but it must be becoming clear to the percipient mind that something is about to happen. In fact, if the load is now displaced a little further outwards, something will happen, that is to say, a situation like figure 4. The stress at the opposite surface of the wall has now changed from compression to tension. We said, however, that mortar cannot be trusted to take tension, and this is generally only too true. What one would expect to happen usually does happen, the joint cracks. Of course it is a bad thing for walls to crack, and it should not be allowed to happen in well-regulated buildings, but it does not necessarily follow that the wall is going to fall down immediately. What is likely to occur in real life is simply that the crack will gape a bit but the wall will continue to stand up, resting on the parts which are still in contact. Figure 5. Figure 3. Load P acting at the edge of the middle third of AB. Figure 4. Load P acting outside the middle third of AB. All this savors somewhat of living dangerously, and one of these days the line of the thrust may stray outside the surface of the wall, when, as a little thought will show, since no tension forces are available, one or more of the joints will hinge about its outside edge and the wall will tip up and fall down. Figure 6. It really will. Figure 5. What really happens as a result of the condition drawn in Figure 4? The joint cracks from B to C, and the load is now carried over the area AC, effectively a narrower wall. At the time when he came to these conclusions, that is, about 1802, Young, a rising man of 29, was appointed to the chair of natural philosophy at the Royal Institution in London. His colleague, and in some sense his rival, was Humphrey Davy, who was made professor of chemistry in the same year at the improbable age of 24. It was the custom of the professors of the Royal Institution, then as now, to deliver series of lectures to popular audiences. In those days, however, these lectures had very much of a television character, and the institution relied heavily upon them for both money and publicity. Figure 6. When load P acts beyond A, i.e. outside the surface boundary of the wall will hinge about A, tip up and fall. Young took his educational mission seriously, and, filled with the enthusiasm of discovery, he launched into a series of lectures about the elasticity of various kinds of structures, with many useful and novel observations on the behavior of walls and arches. The audience at Albemarle Street in those days was a fashionable one and is said to have consisted largely of silly women and dilettante philosophers. Young by no means neglected the feminine part of his audience, and he remarked in his opening lecture, "A considerable part of my audience, to whose information it will be my particular ambition to accommodate my lectures, consists of that sex which, by the custom of civilized society, is in some measure exempted from the more laborious duties which occupy the time and attention of the other sex. The many leisure hours which are at the command of females in the superior orders of society may surely be appropriated, with greater satisfaction, to the improvement of the mind and to the acquisition of knowledge than to such amusements as are only designed for facilitating the insipid." With a range of colorful chemical experiments, was a pushing young particle with what we should now call a television personality. Davy was also remarkably good-looking, and young women flocked to his lectures for reasons which were not always strictly academic. Those eyes, one of them was heard to say, were made for something besides poring over crucibles. The result, in box office terms, could not be in doubt, and we are told that Dr. Young, whose profound knowledge of the subjects he taught no one will venture to question, lectured in the same theatre and to an audience similarly constituted to that which was attracted to Davy. But he found the number of his attendants diminish daily, and for no other reason than that he adopted too severe and too didactic a style. This kind of failure might not have mattered too much if Young could have attracted the interest and support of practical engineers. However, the engineering profession at that time was led, and frequently dominated, by the great Thomas Telford, 1757 to 1834, whose views, as we have seen, were severely pragmatic and anti-theoretical. In consequence, Young resigned his chair almost immediately and returned to his medical practice. The development of elasticity passed, for many years, to France, where, at this time, Napoleon was actively encouraging the study of structural theory. The theory about elastic compression, the middle third and instability which so bored the fashionable females at Young's lectures does really tell us practically all we need to know about the behavior of joints in masonry, provided that we also know the position at which the weight can be considered as acting. In other words, how eccentric is the load. This is best determined by means of what is called the thrust line, that is to say, a line passing down the wall of a building from the top to the bottom which defines the position at which the vertical thrust can be considered as acting in each successive joint. The thrust line is a French invention and seems to have been first thought of by Coulomb, 1736 to 1806. Figure 7. For the simplest symmetrical case, the thrust line passes down the center of a wall. For a very simple symmetrical wall or column or pillar, such as figure 7, the thrust line will clearly pass down the middle of the wall and so there is really no problem. However, in a building with any pretension to sophistication there is most likely to be at least one oblique force arising from the sideways thrust of the roof members, from archways or vaultings or from various other forms of asymmetrical construction. In such a case the thrust line will no longer pass neatly down the middle of the wall but will be displaced to one side, frequently into a curved path such as figure 8*. If, on plotting the thrust line, we find that it is in danger of reaching the surface of the wall at any point, then we shall clearly have to think again, and think hard, because there is a good chance that a building designed like that will fall down. Figure 8. The effect of oblique loading is to deflect the thrust line in this kind of way. One of the things we can do, and it may well be one of the most effective, is to add weight to the top of the wall. What then happens can be represented diagrammatically by figure 9. Contrary to what one might suppose, weight at the top is likely to make a wall more, and not less, stable and will bring an erring thrust line back, more or less, to where it ought to be. One way to do this is simply to build the wall to a greater height than appears to be really necessary, and, in addition, anything like heavy balustrades and copings are a good thing. If it is that sort of building and you can afford it, a line of statues will always help, figure 10. This is the structural justification for the pinnacles and statuary on Gothic churches and cathedrals. They are really up there to say boo to the functionalists and to all the dreary people who bleat too much about efficiency. Figure 9. The effect of an additional load at the top of the wall is to reduce the eccentricity of the thrust line. Conservative principle which makes for safety and ought to be observed, but, in this permissive age, I am afraid that it seldom is. Anyone who looks at a modern housing estate or a new university cannot help seeing that the walls are full of cracks, and, where there is a crack, there must once have been a tension stress. However, although these cracks do a good deal of damage to the plaster work and interior decoration, they seldom constitute any danger to the stability of the main structure. The basic condition for the safety of masonry is that the thrust line should always be kept well inside the surface of a wall or column. Like walls, masonry dams usually fail not from lack of strength but from lack of stability. Again, they are liable to tip up. The sideways thrust on a dam due to the pressure of the impounded water is generally comparable to the weight of the masonry used in its construction. For this reason there are apt to be very large variations in the position of the active thrust line between the full and the empty conditions. With dams, unlike ordinary buildings, one cannot take any liberties at all with the middle third rule. It is quite essential that there should be no cracks of any kind in the masonry, especially on the upstream side. If there are cracks, water under pressure is likely to get inside the structure of the dam and to have two effects, both bad. The first effect is that the flow of water will damage the masonry. To counteract any seepage, arrangements are generally made to drain the interior of large dams. The second effect is more dramatic. It is that the water pressure within the crack will exert a vertical lifting force, about 5 tons per square foot at a depth of 100 feet, i.e. 0 to 5 mn/m2 at a depth of 30 meters, which, acting upon an already rather critical situation, will overturn the dam. It is probable that the destruction of the Moni and Eder dams by the R.A.F. in 1943 was accomplished in two stages, separated by a short space of time. In the first stage, Barnes-Wallis's bombs were dropped against the upstream faces of the dams, where they sank before exploding. When they did explode, the structure of the dams would have been cracked deep down, and after a short delay the actual overturning of the dams themselves was caused by the penetration of high-pressure water into the cracks. Those who have read accounts of the operation will remember that there was an appreciable pause between the explosion of the bombs and the visible failure of the dams. The breaching of these dams, of course, did an immense amount of damage in the Ruhr. The failure of a dam in peacetime is an engineer's nightmare. Even if the dam is made, not from stone, but from unreinforced concrete, it will be unwise to count upon any reliable tensile strength. Thus in all unreinforced dams the thrust line must not move upstream beyond the middle third when the dam is empty nor downstream of it when it is full, and it is just as well to leave something in hand. These requirements usually result in the tapering, asymmetrical shape with which most of us are familiar, Figure 11. However, dams are expensive in relation to the value of the water which they impound, and engineers are continually looking for cheaper ways of making them. A considerable saving in the weight and cost of cement can generally be achieved by reinforcing the concrete with steel rods, especially if the reinforcement is under tension. However, unless the reinforcing rods are anchored to solid rock beneath the foundations of the dam, there is a real danger that the whole dam, reinforcements and all, will be uprooted and overturned. Figure 11. Unreinforced masonry dam. One way of dealing with the situation is shown in Figure 12. Here simple vertical steel tie rods are anchored to the rock beneath and carried up through the concrete to the top of the dam, where they are tensioned by means of a jacking arrangement. It will be seen that these rods are really doing the same job as the angels and pinnacles in a cathedral. Of course, all traditional heavy masonry may be regarded as a structure which is pre-stressed by its own weight. No doubt a line of heavy statues along the top of a dam would be effective and might look rather nice, but I am afraid they would turn out to be more expensive than the steel rods, and so restricts the movement of the thrust line. Although the arch is not quite as old as masonry itself, it is certainly very old. There is evidence of fully developed brick arches, both in Egypt and in Mesopotamia, going back to about 3600 BC. The stone arch seems to have evolved separately, and possibly independently, from the idea of corbelling, that is to say, building out the masonry stepwise from each side until the stones met in the middle. The vaulted chambers, Plate 5, deep under the walls of the Mycenaean city of Tiryns, which were old when Homer marveled at them, are roofed in this way. The postern gate in these immense walls, Plate 6, might be regarded as a development of corbelling. It was probably built before 1800 BC. However, the corbelled asterisk or the semi-corbelled arch, like the gate at Tiryns, is rather a crude affair. Arches soon developed a construction in which the bricks or stones of the arch ring are made slightly wedge-shaped and are called voussoirs. The various parts of a traditional arch are shown in Figure 13. Figure 13. Various parts of an arch. The voussoir at the top or crown of the arch is called the keystone and is sometimes made larger than the rest. Although poets, politicians, and other non-technical people have attributed special qualities to real and figurative keystones, in fact the keystone is functionally no different from all the other voussoirs, and its distinction, if it has any, is purely decorative. The structural function of an arch is to support the downward loads which come upon it by turning them into a lateral thrust which runs round the ring of the arch and pushes the voussoirs against each other. The voussoirs, naturally, push in their turn against the abutments or springings of the arch. The manner in which this process works is pretty clear from common sense. Figure 14. Figure 14. An arch collects the vertical loads and turns them into lateral ones. These lateral loads run round the arch ring and are reacted by the abutments. The arch ring, with its voussoirs, is very much like a curved wall, and the position of the compressive loads at each joint can be indicated by a thrust line in the same sort of way. In this case the thrust line has to curve round and follow, more or less, the shape of the arch. We shall talk about thrust lines and arches in the next chapter. For the moment let us accept that there is a thrust line. Also, as with the wall, we can assume that the voussoirs cannot slide over each other and that the joints cannot take tension. The joints between the voussoirs will behave in much the same way as the joints between the stones in a wall. If the thrust line strays beyond the middle third then a crack will appear. Also, if the thrust line moves to the edge of a joint, that is to say, to the boundary of the arch ring, then a hinge will develop. What makes the arch dramatically different from a mere plebeian wall, however, is that, whereas the wall now falls down, the arch does not. From Figure 15 it can be seen that no fewer than 3 hinge points can develop in an arch without anything very dramatic happening. In fact, a good many modern arch bridges are deliberately built with 3 hinged joints so as to allow for thermal expansion. Figure 15. An arch can put up with 3 hinge points without collapsing, In fact, many modern arches are deliberately built in this way. If we really want the bridge to fall down, then we shall need 4 hinge points so that the arch can become in effect a 3-linked chain or mechanism which is now at liberty to fold itself up and collapse. Figure 16. Incidentally, this is why, if you want to demolish a bridge for good or bad, collapse *, arches do not much mind, and some sort of distortion is quite common. Clare Bridge, for instance, in the backs of Cambridge, Plate 7, is very noticeably bent in the middle because of the movement of the abutments. It has been like that for a long time and is quite safe. In the same way, arches stand up remarkably well to earthquakes and to other kinds of abuse, such as modern traffic. Figure 16. An arch needs to develop 4 hinge points before it can collapse. Altogether, it is not surprising that many of our ancestors were so addicted to arches, for they will probably go on standing up even if you have got all your sums wrong, or not done any sums at all. And, in addition, placed the foundations of the whole thing iij above, as indeed is the case with several of the English cathedrals. It is noticeable that, in ruins, it is generally the arches which have survived best. This is partly due to the inherent stability of arches, though it may well have more to do with the fact that the wedge-shaped stones of the voussoirs are less attractive to the local peasantry than the rectangular ones in the walls. The preservation of the round columns of many Greek temples, long after the ashlar of the walls has been stolen, is no doubt due to similar causes. It is generally easier to keep the thrust line well inside a wall or an arch if the masonry is thick. But of course solid brick and stonework are expensive. To get extra thickness at a low price, the Romans introduced mass concrete. This was usually made by mixing pozzolana, pulvis puteolanis, a natural earth which is fairly common in Italy, with lime, and adding sand and gravel. If walls and arches are made thicker, they are generally more stable and may not need to be made so heavy. If less weight of material has to be transported and handled, then the cost of construction is likely to come down. Vitruvius, Fluid 20 BC, who was a very distinguished architectural writer as well as an artillery officer, tells us that in his day low-density concretes were often made by incorporating pumice powder. The Great Dome of the Hagia Sophia in Constantinople, AD 528, is made in the same way. Reduction of weight and cost can be taken still further by incorporating empty containers of one sort or another in the concrete. In the ancient world, the very extensive and prosperous wine trade was carried on by means of amphorae. These large earthenware containers were strictly non-returnable and they tended to accumulate in embarrassing quantities. The obvious solution was to cast them into concrete, and in fact many late Roman buildings are made in this way. In particular, the beautiful early. Although some structures are alleged to be sustained by the power of faith and others to be held together entirely by paint or rust, unless a designer is totally irresponsible. He likes to have some kind of objective assurance about the strength and stability of whatever he is proposing to make. If one is unable to do the right sort of modern calculations, then the obvious thing to do is either to make a model or else to scale up from some previous smaller version of the structure which has proved to be successful. This, of course, is pretty well what people used to do down to quite recent times. Perhaps they still do. The difficulty is that models are all very well if one just wants to see what the thing will look like, but they can be dangerously misleading if they are used to predict strength. This is because, as we scale up, the weight of the structure will increase as the cube of the dimensions, that is, if we double the size, the weight will increase 8-fold. The cross-sectional areas of the various parts which have to carry this load will, however, increase only as the square of the dimensions, so that, in a structure of twice the size, such parts will have only 4 times the area. Thus the stress will go up linearly with the dimensions, and, if we double the size, we double the stress and we shall soon be in serious trouble. The strength of any structure which is liable to fail because the material breaks cannot be predicted from models or by scaling up from previous experience. This principle, which was discovered by Galileo, is known as the square-cube law, and it is one good reason why vehicles and ships and aircraft and machinery need to be designed by proper modern analytical methods. This is probably why such things were so late in developing, at least in their modern forms. However, we can neglect the square-cube law with most masonry buildings because, as we have said, buildings do not normally fail by reason of the material breaking in compression. The stresses in masonry are so low that we can afford to go on scaling them up almost indefinitely. Unlike most other structures, buildings fail because they become unstable and tip up, and for any size of building this can be predicted from a model. Plate 1 Chapter 2 Each of the 4 columns which support the 400-foot, 120-meter, Tower of Salisbury Cathedral is very noticeably bent. Masonry is much more elastic than is generally supposed. Plate 2 Chapter 4 Stress concentration at a crack tip. The shear stress in a transparent material is revealed by polarized light. The bands in this photograph are, in effect, contours of equal shear stress. Plate 3 Chapter 8 Rubber has a sigmoid stress-strain curve like Figure 4, Chapter 8. A tube made from such a material will not distend evenly under pressure but will bulge into an aneurysm. This is why artery walls do not have rubbery elasticity. Plate 4 Chapter 8 Artery walls in other living soft tissues have a special kind of elasticity like that in Figure 5, Chapter 8. The artery wall is constructed partly of elastin reinforced by kinked collagen fibers. This helps to produce the required safe type of elasticity. The artery tends to flatten when it is emptied of blood after death. Plate 5 Chapter 9 Corbelled vault at Tiryns, c. 1800 BC. Corbelled arches and vaults preceded the true arch. Plate 6 Chapter 9 Semi-corbelled postern gate at Tiryns. These walls were old when Homer marveled at them. Plate 7 Chapter 9 It is very difficult to get a true arch to fall down. The foundations of Clare Bridge, Cambridge, moved a long time ago, but the bridge is perfectly safe though the arch has distorted. Plate 8 Chapter 9 Part of the enormous temple of the Olympian Zeus at Athens. It was built in the Corinthian style by the Emperor Hadrian about AD 138. One of the architraves can be seen to be cracked. Note the walls of the Acropolis, which tower above Hadrian's temple. Plate 9 Chapter 9 Skeletons of A. Gibbon and B. Gorilla, to scale. The square cube law applies more to beams than to columns. Thus as animals get larger, their ribs and limb bones tend to become thicker in proportion to their vertebrae. Plate 10 Chapter 10 Brunei's Maidenhead Bridge, 1837, has the longest and flattest brick arches in the world. Many people predicted that the arches would not stand, but they are still there today carrying trains 10 times heavier than Brunei's. Plate 11 Chapter 10 Telford's Mina Suspension Bridge, 1819. The span of 550 feet, 166 meters, is approaching the limit for wrought iron suspension chains. Plate 12 Chapter 10 The Severn Suspension Bridge. High tensile steel cables with 10 times TNE tensile strength of wrought iron enable bridges nearly 10 times as long as Telford's Mina Bridge to be constructed. Plate 13 Chapter 11 Where there are no side aisles, as in King's College Chapel, Cambridge, the buttresses can be carried straight up without further complication. Plate 14 Chapter 11 HMS Victory. Her masts form a superb example of a trussed cantilever structure of very large dimensions. Plate 15 Chapter 11 The American railways could be built quickly and cheaply because wooden trestle bridges were used very extensively to save the cost of earthworks, c. Plate 16 Chapters 11 and 13 Stephenson's Britannia Railway Bridge, 1850, used wrought iron box beams. The trains ran inside the beams. Much trouble was experienced in preventing the thin iron plating from buckling. In front of the bridge are grouped a number of contemporary engineers. Robert Stephenson is seated in the left center and I.K. Brunei is seated on the extreme right. Plate 17 Chapter 12 The bias cut, invented by Mille Vianney, exploits the low shear modulus and high Poisson's ratio of certain square weave fabrics in the 45 degrees direction. This is one of the earliest Vianney bias cut dresses. AD 1926. Plate 18 Chapter 12 Contemporary square cut dress, also Vianney. Note low Poisson's ratio and lack of clinging effect. The vertical creases are caused by the existence of a Wagner tension field. Plate 19 Chapter 12 Wagner tension field in the fuselage skin of a ferry Rotodyne. Plate 20 Chapter 15 The Tacoma Narrows Bridge is a classic example of a suspension bridge built with inadequate torsional stiffness. Known as Galloping Gertie, it displayed serious oscillation when exposed to quite moderate winds, and very soon wriggled and buckled itself into failure in a wind of only 42 m.p.h. Plate 21 Chapter 16 The first real mass production machinery to come into use was the block-making equipment at Portsmouth Dockyard. Both the machinery and the blocks themselves may be regarded as handsome, perhaps as beautiful. Plate 22 Chapter 16 The classical form of steam yacht developed by George Lennox Watson is one of the most beautiful of all ship conventions. But it is largely non-functional. The ends and especially the bowsprit represent sailing ship practice. That is to say they are skymorphs. S.Y. Nolan. No single photograph can do justice to the Parthenon, but this picture of part of the southwest corner may give some slight impression. Note that the left-hand lintel is cracked. For this reason the architraves are in triplicate. Note also numerous skymorphs or vestiges of wooden construction, e.g., triglyphs, mutoids, etc. Plate 24 Chapter 16 Unlike the classical Greeks 1,000 years later, the Mycenaean Greeks, c. 1500 BC, designed their buildings to take account of the low tensile strength of stone. The lintel of the Lion Gate at Mycenae is provided with a triangular block of stone to relieve the tensile loads. The architrave is a single block and carries very little stress. The distance between the centers of the chariot ruts. Balance. Thus, if a small building stands, a scaled-up version of it can also be relied upon to do so, and the mystery of the medieval builders consisted in reducing this experience to a series of rules and proportions. However, that they also used models sometimes 60 feet, 18 meters, long made from masonry or plaster is well established. This mode of procedure generally worked even for structures of incredible complexity, such as Reims Cathedral, Figure 18. Figure 17. The stability of a building is like that of a balance, it is not affected by scaling up. The Greeks of the classical period abandoned the arch for most of their serious architecture, preferring to use stone beams or lintels. In such beams the tensile stresses were relatively high and often too near the limit for safety. A considerable number of these architraves were cracked, even in ancient times. This is why iron reinforcement was used in the marble beams of the Propylaea, for instance. What saved the Doric temple from structural collapse was that the stone beams were short and deep and, as they cracked, they turned themselves into arches. Figure 19, Plates 8 and 23. Figure 18. Reims Cathedral, Flying Buttresses, after Viollet-le-Duc. Greek Trabeate * architecture required very large blocks of stone. When civilization decayed, the transportation of large masses became increasingly difficult, and this may have been one, strictly practical, reason why the medieval builders favored Gothic arches and vaults, which can be made from quite small stones. Figure 19. If a short stone lintel or architrave cracks on the tension face, it may turn itself into a 3-hinge arch and continue to support the load. As Sir John Soane pointed out nearly 200 years ago in his lectures on architecture, in spite of the limitations of stone beams, the size of ancient buildings was often greater than that of corresponding modern ones. The Parthenon, for instance, is considerably bigger than St. Martin in the Fields. Nevertheless, the Parthenon, about 230 by 100 feet, 69 by 30 meters, is small compared with Hadrian's Temple of the Olympian Zeus close by, which measures 359 by 173 feet, 108 by 52 meters, and would fill most of Trafalgar Square, Plate 8. Yet Hadrian's Temple, in its turn, is dwarfed by the walls of the Acropolis, which tower high above it. Again, for sheer size, many of the Roman bridges and aqueducts are impressive by any standards. These ancient constructions have more often been destroyed by men than by nature, and some of them are still in good condition today. However, in all these works the ancients were more or less following familiar examples. When they were unable to do so they were apt to come badly unstuck. Not only are ancient ships and vehicles almost pathetically small and fragile to our modern eyes, but new and unconventional buildings such as the Roman insulae, which were tall blocks of flats, fell down with such depressing frequency that the Emperor Augustus was compelled to pass laws restricting their height to 60 feet, 18 meters. The backbones of people and animals consist of a series of short, drum-like vertebrae, made from hard bone. They are separated from each other by the intervertebral discs, which are made from comparatively soft material and thus allow a limited amount of movement between the vertebrae. As a rule, the spine is subject to an overall compression arising both from the weights it has to carry and also from the pull of the various muscles and tendons. In young people the material of the discs is flexible and tough, and it can withstand considerable tensile stresses if it has to. So much so that, if the spine is damaged by tensile forces, fracture is likely to occur in the bone rather than in the discs. After the age of about 20, however, the disc material gets progressively less flexible and also considerably weaker in tension. As we get more venerable, therefore, we approach a situation in which our backbone is getting rather like a column in a church or a temple. The vertebrae represent the stone drums and the discs the weak mortar. Although the discs can still, at a pinch, take a certain amount of tension, this is, on the whole, a situation to be avoided. Therefore, for middle-aged people, it is wise to keep the thrust line as near the middle of the backbone as possible. This is why there is a right and a wrong way of lifting a heavy weight. If we lift the weight in the wrong way, excessive tensile forces are set up in the joints and one of these may break. The result is likely to be a slipped disc or one of the other manifold and rather mysterious back troubles which we include under the name of lumbago, which is apt to be surprisingly painful. Insofar as a backbone behaves like a wall or a masonry column and departure from the middle third rule represents some sort of limiting condition, then the same kind of rules apply to scaling up an animal as we have seen apply to scaling up a building. Thus, if we start with a small animal and progressively increase its size, the necessary thickness of the vertebrae will remain in due proportion. Most of the other bones, however, such as the ribs and the bones of the limbs, are subjected chiefly to bending rather like the lintels of a temple, and the loads upon them are likely to be proportionate to the mass of the animal. It follows, therefore, that such bones have to be made disproportionately thicker. If we look in a museum at the skeletons of a series of similar animals of increasing size, such as monkeys, it does appear that, whereas the dimensions of the vertebrae of little monkeys and middle-sized monkeys and gorillas and men are roughly in proportion to the height of the animal, the limb bones and, especially, the ribs become very much thicker and heavier, for the size of the animal, as the scale increases. Plate 9. In this respect nature seems to be cleverer than the Roman architects, who, as they increased the size of their temples, abandoned the rather stocky Doric proportions and built, as a rule, in the florid imperial Corinthian style, with slender architraves which frequently broke. Note that Genesis 11 specifically says, "Let us make bricks and bake them hard." There was no question of using cheap mud bricks as the Egyptians did. This seems to be an early example of the Concorde syndrome. Of the Abbey Church of Saint Denis, in France, during the 12th century, we read, "Such a the Royal Society. He is said to have been offered a bishopric if he would take holy orders. As a great man who had risen from humble beginnings, he behaved rather badly to a coal miner called George Stephenson, but rather well to a blacksmith's son called Michael Faraday." That this is so can be checked by applying the parallelogram of forces, whose acquaintance can be renewed in the pages of elementary textbooks on mechanics, at each level in the wall. The parallelogram of forces is supposed to have been invented by Siemens Devine in 1586. The absence of the concept of the resolution of forces is one reason why it is impossible that either ancient or medieval architects could have designed their buildings in the modern way. There are really several thrust lines, and all of them need to be kept inside the surface of the wall. The passive thrust line. This is the thrust line which results from the weight of the wall itself and of all the things which are permanently attached to it, such as floors and roofs. The active thrust lines. These are the thrust lines which result, not only from the permanent parts of the building, but also from all the transient loads which might be applied to it by wind pressure or the weight of things like water, coal, snow, machinery, vehicles, people and so on. The shapes of the various active thrust lines define the ways in which a masonry structure can safely be loaded. This is one of the reasons for the modern fashion of not plastering the insides of buildings. The true arch seems to be an old world development. The indigenous civilizations of Mexico and Peru built their large buildings using only the corbelled arch. This is the rationale of mining or sapping under fortress walls during siege warfare. When the end of the tunnel was beneath the foundations of the wall, its roof was supported by wooden props. At an appropriate moment a fire was lit so as to burn through the props, when it was hoped that the wall would collapse. The function of both wet and dry moats was chiefly to prevent sapping. The famous Bristol Channel pilot cutters, c. 1900, were ballasted with concrete which was run into the bilges. The concrete amidships, which needed to be heavy, was made up with scrap iron and boiler punchings. The concrete in the ends of the ship, which had to be light, was filled with empty beer bottles. For the plinths of statues and urns in my garden I generally use a mixture of old chicken wire, empty wine bottles and concrete. It seems to work very well. Asterisk from the Latin trabs, a beam. Or Saint Benezet and Saint Isambard. London Bridge is falling down, falling down, falling down. London Bridge is falling down. My fair lady. Build it up with brick and stone, brick and stone, brick and stone. Build it up with brick and stone. My fair lady. Set a man to watch all night, watch all night, watch all night. Set a man to watch all night. My fair lady. The more we think about this familiar nursery rhyme, the more eerie it appears to be. Though it cannot be traced with certainty much before the 17th century, it is undoubtedly very much older, and the Oxford Dictionary of Nursery Rhymes devotes several rather gruesome pages to it. All over the world bridge building used to be associated with children's dances on Danse, on Danse. 9 Sur le Pont d'Avignon and with human sacrifices which are not just legends. At least one child's skeleton has been discovered immured in the foundations of a bridge. Asterisk perhaps for this reason, special orders of bridge-building friars Fratres Pontifex were founded during the Middle Ages in various parts of Europe. They produced a saint, Saint Benezet, who is supposed to have designed the Pont d'Avignon. Like Telford, in a later age, he had been a shepherd boy, and it is rather a nice thought that, dispensing with the sacrifices, he kept the children's dances and the tune to which French children dance to this day. The French branch of the Order of Bridge-Building Friars had a monastery, near Paris, with the charming name of Saint Jacques de Hautpas. In practical terms, the purpose of a bridge is to enable heavy objects, such as vehicles, to cross over some kind of gap or chasm. Provided that the weight is supported in a safe manner, it usually does not matter very much by what technical means this is done. As it turns out, there is a very considerable variety of structural principles which can be employed. The method which is actually chosen in any given case depends not only upon the physical and economic conditions but also upon the fashion of the day and the whim of the engineer. Almost every conceivable way in which a bridge could possibly be made has actually been tried, at one time or variety. They provide a very interesting display of different structural principles. With most other artifacts, the vital structure is hidden away behind paneling or insulation or wiring or gadgets of one kind or another and is not easily seen or inferred. One virtue of bridges is that both the structure and the way in which it works are clear for all to see. Arch bridges have always been popular and, in various forms, they are still very much in fashion. A simple masonry arch can quite safely be built with a span of well over 200 feet. 60 meters. For most sites, if there are objections, they are likely to be associated with the cost or with the rise of the arch and with the load on the abutments or foundations. If we are concerned with the plain, semicircular masonry arch which was widely used in Roman and medieval times, then one of the facts of life is that the rise of the arch must be about half its span. Thus a 100-foot span will call for a rise of at least 50 feet, in practice rather more. This is all very well if the bridge is spanning a ravine which is more than 50 feet deep, because the arch can then be sunk so that its crown is level with the roadway on either side. However, if the bridge is to be built on flat ground, then we have the alternatives, on the one hand, of a humpbacked bridge, which is inconvenient and dangerous, or, on the other, of having to build long and expensive sloping approaches. The problem became particularly important with the coming of railways, because trains don't like humpbacked bridges or indeed gradients of any kind, and the expense of earth moving to make embankments for a flat approach is a serious matter. One way of getting round the difficulty, at least to a certain extent, is to build a rather flat arch with considerably less rise. In 1837, faced with the problem of getting the Great Western Railway across the Thames at Maidenhead, Isambard Kingdom Brunei built a bridge of 2 brick arches, each with a span of 128 feet and a rise of only 24 feet. Plate 10. Both the public and the experts were horrified, and the papers were full of letters prophesying that the bridge would never stand. To keep the correspondence and the publicity going, and perhaps to gratify his sense of humor, Brunei delayed removing the wooden centering or false work on which the arches had been erected. Naturally, it was said that he was frightened to do so. When, after about a year, the centering was destroyed in a storm, the arches stood perfectly well. Brunei then revealed that the centering had, in fact, been eased to a clearance of a few inches soon after the brickwork was in place and had been doing nothing at all for many months. The bridge is still there today, carrying trains about 10 times as heavy as Brunei ever intended. When we flatten the shape of an arch, so as to reduce the rise in proportion to the span, the compressive thrust between the voussoirs of the arch ring is considerably increased, as we should expect. However, the compressive stresses are still, as a rule, well below the crushing strength of the masonry, and the voussoirs of the arch are seldom in any danger of being broken. Although the deflections which occur when the arch settles after the centering is removed may be quite large and often amount to several inches. Any real damage to a flat arch, however, is most likely to be a consequence of the greater thrust which must come upon the abutments. If the foundations are of a solid material, such as rock, all will be well, but if they are upon soft ground there may be serious trouble if they yield too much. Unfortunately, the need for a long, flat arch is most likely to occur when we are bridging rivers which flow across a level and boggy country. It is for these reasons that bridges are often built with many small arches, in fact nearly all long. Some of the objections to arched bridges can be got over by making them from less traditional materials. By the 1770s people like John Wilkinson, 1728–1808, who had greatly cheapened the manufacture of cast iron by improvements to blast furnaces, began to cast voussoirs from iron. Cast iron is a totally different kind of material from wrought iron and steel because, unlike these substances, it is very brittle. It resembles stone in being strong in compression but weak and unreliable in tension, and so, in building construction, it has to be treated rather like masonry. An advantage of cast iron is that it is possible to cast architectural members, such as voussoirs, in the form of an open, trellis-like framework, so that there can be an enormous reduction in weight, as compared with traditional masonry. Furthermore, it is generally cheaper to cast iron than to carve stone, and, before taste degenerated around the time of the first Reform Bill, these iron castings were often of very attractive shape. The benefit of cast iron to bridge building was twofold. In the first place, there was a saving in labor and transport costs. But more significantly, the reduction in the weight of arches diminished the magnitude of the thrust upon the abutments and thus enabled engineers to build flatter arches with cheaper foundations. Curiously, one of the first people to take advantage of this technique was the American Thomas Paine, 1737–1809, who is famous in the history books as the author of The Rights of Man. Paine planned to build a great cast iron bridge, which he had designed himself, across the Schuylkill River, near Philadelphia. He came to England to order the castings, and while they were being made he decided, as a supporter of the French Revolution, to pay a visit to his Jacobin friends in Paris. These gentlemen put him in prison and very nearly guillotined him. He was just saved by the fall of Robespierre. As a result of the delay, Paine's finances collapsed and the castings were sold off to build a bridge over the Wear at Sunderland. The arch, which was finished in 1796, had a clear span of 236 feet with a rise of only 34 feet. The reason why Brunei did not use cast iron for the Maidenhead Bridge 40 years later was probably that he was afraid that the vibrations of the trains would crack the brittle cast iron. In any case, his brick arches worked very well. During the 19th century a great many cast iron arch bridges were built. Although nearly all of them were successful, the method is scarcely ever used today, chiefly because there are now cheaper ways of doing the same job. Unfortunately, a very flat cast iron arch looks, superficially, rather like a beam. See Chapter 11. Structurally the two are quite different, since the arch is, or should be, entirely in compression, whereas the underside of a beam is in tension. The material can be relied upon to carry tensile stresses, then a beam is often lighter and cheaper than an arch, for a comparable service. Some of the early engineers, notably Robert Stephenson, 1803–59, were tempted by this prospect of economy to venture into using cast iron beams. Because of Robert Stephenson's outstanding professional reputation, the railway companies were persuaded to build several hundred cast iron beam bridges. However, as we have said, cast iron is weak and treacherous in tension, and these bridges turned out to be very dangerous indeed. In the end, every one of them had to be replaced and a modern tendency in building large arch bridges is to use a suspended roadway. If we split the arch ring into two parallel elements, which are made from steel or reinforced concrete, then we can hang the roadway from the arches, at any level we like, in much the same way as is done in suspension bridges, figure 1. There is then, of course, no restriction on the rise of the arch. Figure 1. Arch with suspended roadway. The Hell Gate Bridge in New York, 1915, which is 1,000 feet, 300 meters, span, and the Sydney Harbour Bridge, 1930, which has a span of 1,650 feet or 500 meters, are steel bridges of this type. In such bridges the main loads are carried entirely in compression in the arches, and the hanging roadway is free from longitudinal stresses. In big bridges the thrust upon the abutments is therefore considerable, and very reliable foundations are needed. Both the Hell Gate and the Sydney Harbour bridges are founded on solid rock. Masonry arches have a number of advantages. As we have seen in the last chapter, they are comparatively easy to design, since one can generally scale up from previous experience quite safely. In fact, as Professor Heyman remarks, it is very difficult to design an arch which will actually fall down. This feat was, in fact, achieved by a certain William Edwards at Pontypridd in 1751, but I do not think there is any record of its happening since. Again, arches are not unduly sensitive to a reasonable amount of movement in the foundations. However, foundations of some sort there must be, and on soft ground they have a way of being both troublesome and expensive. Furthermore, although the maintenance cost of masonry is usually low, the first cost has always been high, and this is particularly the case with large bridges, which need elaborate centering during erection. For these reasons there has always been a demand for something cheap and cheerful in the bridge line. In primitive countries suspension bridges of various sorts were fairly common. These were made from rope or other kinds of vegetable fiber. Rope suspension bridges were also used by military engineers for temporary bridging, notably by Wellington's sappers during the Peninsular War. However, although rope is a strong and reliable material for carrying tension when it is new, ropes made from plant fibers deteriorate fairly quickly in the open and become undependable, as the more interesting personalities in the neighborhood of the bridge of San Luis Rey discovered. Asterisk: for a permanent suspension bridge, cables of iron or steel are necessary. Cast iron was far too brittle and steel was not commercially available until relatively recently, but wrought iron is fairly strong and very tough, also it is exceptionally resistant to corrosion. Although a footbridge 70 feet, 20 meters, long, made with iron chains, was erected over the Tees in 1741, wrought iron was generally too expensive to be used at all widely in bridge building until the puddling process was introduced about 1790. After this, wrought iron chains became comparatively cheap. In the Tees bridge the flooring was attached directly to the chains in the primitive manner, so that the bridge was impassable to vehicles and must have been both steep and alarming for pedestrians. The modern system of supporting the cables from high towers and hanging the roadway below the cables, figure 2, was invented by James Finlay, of Pennsylvania, who began to build bridges of this kind around 1796. Figure 2. The modern form of suspension bridge, with a level roadway hung from the cables, was invented by James Finlay about 1796. Telford, whose bridge across the Mina Straits, Plate 11, was finished in 1825, it has a center span of 550 feet, 166 meters, by far the longest then in existence. Telford's chains, like all the suspension chains used in bridges at that time, were made from flat plates or links, joined by bolts or pins, very much like the links of a modern bicycle chain. The concentration of stress at the pin joints calls for a tough and ductile material, such as wrought iron, and indeed chains of this type have been very successful and have seldom given any trouble. Although wrought iron is reliable in tension it is not especially strong, and Telford wisely kept the highest nominal stress in his chains down to about 8,000 psi, 55 mN/m2, which is less than a third of the breaking stress. In these circumstances a great deal of the strength of the chains was devoted to supporting their own weight, and Telford was of the opinion that the Mina Bridge represented about the maximum safe span for a suspension bridge. Using the materials of the day. Although Brunei eventually showed that Telford was being rather cautious, Brunei's Clifton Bridge has a span of 630 feet or 190 meters. Yet for many years the span of the Mina Bridge remained a record, and, in any case, the limitations of wrought iron chains were clearly within sight. The recent fashion for road suspension bridges of great length is made possible by the availability of high-tensile steel wire. This material is very much stronger than wrought iron or mild steel and can therefore support a much greater length of its own weight. High-tensile steel is more brittle than wrought iron, but this can be accepted, since the cable is continuous and does not have to have links with pinch joints, which are particularly vulnerable to cracking. Again, instead of having only 3 or 4 plate links in parallel with each other in each element of a chain cable, the wire cables are woven from many hundred separate wires, so that the failure of any individual wire is not likely to be dangerous. Plate 12. As an example of the sort of thing one can do nowadays, the new Humber motorway bridge has a clear span of 4,626 feet, 1,388 meters, which is over 8 times the length that Telford thought practicable. This is made possible by the fact that the suspension wires operate, quite safely, at a working stress of 85,000 psi or 580 mN/m2, which is more than 10 times the stress in Telford's wrought iron chains. The cables of a suspension bridge take up the best shape automatically, because a flexible rope has no choice but to comply with the resultant of all the loads which are pulling on it. We can therefore determine the shape of the cables for a suspension bridge either by loading a model of it, as Telford did, or else by means of a fairly simple exercise with a thing called the funicular polygon on the drawing board. This is useful in designing suspension bridges. For instance, we need to know the right lengths for the hangers for the roadway, but it is also useful in designing arches. If we look at a suspension bridge and then at an arch, it does not need much imagination to see that the suspension bridge is really an arch turned upside down or vice versa. In other words, if we change the sign of all the stresses in an arch, that is, if we turn all the compressions into tensions, then these tensions could be carried by a single curved rope, which may be regarded as defining a thrust line in tension. By doing this we can arrive, comparatively painlessly, at the compressive thrust line for an arched bridge or a vaulted roof. When we do so we may get various shapes of thrust line which will vary a bit according to the details of the loading, for instance the presence or absence of traffic on the bridge. Any of these thrust lines will be safe, provided that it lies wholly within the intended shape of the arch ring, if not, not. It is sometimes said, by slightly superior people, that the thrust line of an arch obtained in this way has the shape of a catenary, and that a round arch is therefore wrong. This is by no means always the case, and in many instances the thrust line is quite near enough to an arc of a circle to justify the Romans in their highly durable semicircular arches. However, if one wants to make a really thin arch, as is the custom with modern reinforced concrete bridges, then one had better get the shape just right, for there is very little room for the thrust line to wander about. Although the suspension bridge got off to a flying start at the beginning of the 19th century, its development was interrupted for about 100 years by the coming of the railways. Most of the 25,000 major bridges which were built in England during the Victorian era were railway bridges. The suspension bridge is a highly flexible structure, and it is liable to deform dangerously under large concentrated loads. This characteristic does not matter very much for road bridges *, but trains are generally about 100 times as heavy as carts or lorries, and so the deflections they cause are likely to be 100 times as great and therefore unacceptable. The few railway suspension bridges which were built in England were conspicuous failures. The Americans, who had wider rivers, and at that time less money and more faith, persisted with them for a while but had to give most of them up in the end. There was therefore a need for bridges which were not only light and cheap but also rigid and suitable for large spans. This led to the development of what is called the tied arch or bowstring girder, figure 3. An arch, of course, is pretty rigid, but it thrusts outward on its abutments with a very considerable force. This may not matter if these abutments consist of nice firm rock, but it is awkward in many of the situations which may arise in railway construction. It is particularly inconvenient if it is required to perch an arch, or a series of arches, on top of tall and slender piers which may be in no position to resist large lateral loads. Figure 3. The bowstring girder, or tied arch, relieves the abutments of lateral thrust. It was popular with Victorian railway engineers. However, this is just what the Victorian engineers so often wanted to do, for they frequently carried their railways boldly across deep valleys, sometimes at a height of 100 feet or more. One way of solving the problem is to tie the two ends of the arch together by means of a tension member. This can be done by using a suspended roadway, which in this case is made to work for its living, the roadway itself is put into tension. The bowstring girder looks superficially like an ordinary arch with a suspended roadway, but its manner of working is quite different. Now there is no sideways push or pull upon the foundations, which have only to support the vertical downward load arising from the actual weight of the girder and any vehicles which may be on it. In fact, the whole affair can be mounted on rollers instead of on rigid foundations, and this is often done, mainly to allow for thermal expansions and contractions raised into position by means of jacks. This is just what Brunei did with the spans of the Salt Ash Bridge. As we shall see in the next chapter, the tide arch is really yet another member of the prolific family of trusses or lattice girders with which structural engineering is so thickly populated. Asterisk at the Roman fort at Lowberry Hill, in Berkshire, a mile or so from where I am writing this chapter, the body of a woman was discovered concreted into the foundations. The practice has lasted into modern times. In 1865 it was alleged that in Ragusa Christian children were being kidnapped by Mohammedans in order to immure them in the foundations of fortifications. Even in England, as late as 1871, a certain Lord Lee was seriously suspected of having built an obnoxious person into the foundations of a bridge at Stoneleigh in Warwickshire. Asterisk the Bridge of San Luis Rey, Thornton Wilder, 1927. The New Science of Strong Materials, Chapter 10. Asterisk all Telford's bridges were road or canal bridges. The Americans made fairly extensive use of suspension bridges for canal aqueducts. The water channel was carried in a suspended wooden flume. Naturally there was no change of net load and therefore no change of deflection when a barge passed over the bridge.